the previous discussion, which is the model for point positioning with code pseudo ranges, is clear to all. And if there is any question, you can ask right now. There's no problem in that. Any questions? Okay, so now let us see this model for point positioning with carrier phases. Is that the model which is there? You can see this model, which is lambda phi ijt is equal to rho ijt plus c delta rho ijt plus lambda n ij. So this is the compressed format or compressed model which is written for the carrier phase equation, ignoring all other terms. So if you recall that in your previous just previous lecture, we were discussing about the models, but in the last Thursday we were discussing about the code observable equation and the phase observable equation, where we have discussed also the ionospheric term, tropospheric term, the delays term. And many of you would think that why we are ignoring the other error parts apart from this clock. We are ignoring because we considering this error component, which is considered that for the clock error, that component is something in the ranges of about 300 kilometers. So roughly ignoring that smaller error contribution in the range, we can write this equation as lambda phi ij is equal to rho ij plus c delta ij plus lambda n ij. Okay, so having said that, you can understand lambda phi ij is the phase observable, that is in meters. Okay, you have this phase observable, but now this lambda phi ij make it the units in meters. Let's say if only phi is written, that would be in cycles, but the moment you multiplied this it with lambda, this becomes the so-called your lambda phi ij, which becomes in meters. So obviously the right hand side rho ij geometric range, that is in meters. So individually I'll name it. Lambda phi ij is this the carrier phase observed in meters. Rho ij is geometric range between I and j in meters. Then c delta rho c delta ij in meters, plus the ambiguity term, which is lambda nij. What do you say to the ambiguity? Just recall in your mind that it is the initial integer ambiguity which is unknown before the receiver is locked with the satellite. Just recall it in the sense that it is the ambiguity or initial number of phase cycles which are unknown to the receiver. So now you can open it up again, the delta ij term, which is delta I minus delta j. You know that this is the receiver clock offset and satellite clock offset with respect to GPS time frame. Okay, so the lambda phi ij is written in opening up in the second uh, uh, this block of the equations, is that rho ijt plus c delta it minus c delta jt plus lambda nij. Any problem in that? Just look at this the first equation of the second block for time moment. Just observe it. If you have any problem, you can ask. So I hope it is clear. The second equation follows with the similar to your previous equation, where we are opening up the first geometric term, and by linearizing we have done it, is that rho I j naught t minus, this is the coefficient of the first partial differentiation, this is the coefficient of the second partial differentiation, and this is the coefficient of the third partial differentiation. Just observe it. Now can you show it? Now can you see it, this equation? So in this equation, you have this three components which are written as the partial differentiation with respect to delta x, delta y, delta z, or simply with respect to x, y, and z. Now, what we are doing, since we have to make the equation in the v is equal to ax minus l form, so what we will do, we will reshuffle the left hand side and right hand side just based on our requirement. So left hand side would become the observable. So what you have the carrier phase observable. Then the rho ij naught t, which is the initial geometric range with respect to the initial points that you have. Okay. Then the clock error of the satellite, you know it. So left hand side would become these three terms. The right hand side would again similar to your previous plus the lambda n ij. Okay. Now again just think in that direction and observe that what is L, what is A x, what is A y, what is your A z, and similarly for four set right you can form the equation. Any, just observe it and write down on your note sheet also at the same time. That will make you a little more comfortable about the components which you can by just looking at you will not be more comfortable. Just write it down. I'm giving you a little more moment for that. You just write it down and you can observe it.
Sir, here in third box
Uh-huh.
where AXI, AYJ, and AZJ is written, in
Huh.
that first line, LIJT is equals to PIJT is written. They have,
Very nice observation. It is wrong. It is lambda phi ijt. Okay.
okay, sir.
Very nice observation. Good. Okay, so any questions before we move on to the next slide?
Sir, one question is there, sir.
Ah,
Like taken from right side to left side that C delta JT. Sir, why we have not
hmm.
taken that C delta IT? Because it is because it is receiver term and we are getting observations from this. Is it so?
nahi, it is because satellite informs you about their error in the clock with the help of navigation message. You can get the parameters by which you know how much drift is there in that clock. That's why it is on the left hand side has become observable. But the receiver clock error is a very poor standard clock. The offset which is there in the receiver clock is never known to you. You have to estimate the error.
Okay, sir. Got it.
Now this L, A, and X, you can write it down, and that becomes your V is equal to AX minus L kind of format, which you can simply start working with. Obviously, what is more important is that you should also understand the number of observable required, number of unknowns available, etc., etc. So for three epochs, there will be 12 equation and 10 unknown. The solution of this over-determined system at three epochs can be performed by least square adjustment. And we all know about the procedures and parameters corresponding design metrics. So this equation is extended for four satellite, but in three epochs. That is T1, T2, T3. Now please answer this point, why N1, N2, N3, and N4 doesn't have a T1, T2, T3 component. Just answer this, any of you.
सर क्वेश्चन एक और बता दीजिए.
Why the N1, N2, N3, and N4 doesn't have a T1, T2, T3 component?
सर ये जो लेमडा फाइव आई जे टी है सर, ये कैरियर फ्रेज ऑब्जर्व करने से इसमें इसकी जो वैल्यूज है सर मीटर्स में आती है। सर जो
हम्म,
एन मल्टीप्लाई होगा वो लेमडा से होगा और लेमडा विल बी इन मीटर्स। सर टी कंपोनेंट आएगा तो वो उसका डायमेंशन मैच भी नहीं करेगा।
नहीं 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 नहीं, आप N1 N2 N3 N4 देख पा रहे हैं?
यस सर।
कहाँ पर है वो?
सर एक्स में।
एक्स में, ठीक है। अब
यस सर।
हाँ, अब आपको यही देख करके यहाँ बताना है कि जो आपका N1 के साथ T नहीं लिखा हुआ है, T1 T2 T3, N2 के साथ T1 T2 T3 नहीं लिखा हुआ है, उसका रीजन क्या है? और आलोक बताइए भाई।
Sir, because once a satellite is locked to a receiver, the initial number of cycle which are unknown are will be fixed now.
Yes, when the satellite is logged with the satellite receiver, the initial number of cycles, that's the terminology for ambiguity. This N is called as ambiguity. So this value for N1, N2, N3, and N4 is fixed until the loss of lock is not happened. That means if there is a loss of lock, if there is a connectivity issue between satellite and receiver, then this will another time change. Otherwise, this will remain fixed. However, the receiver clock error would be fluctuating with respect to the time domain. चलिए, any more questions? चलो एक कंपैरिजन कर लेते हैं, कंपैरिजन ऑफ कोड एंड कैरियर मेजरमेंट्स. So carrier wavelengths, which is 19 centimeter for L1, are much shorter than CA code chip length 293 and hence can be measured more accurately. अब आप इसको ऐसे समझ सकते हैं that we have told you in the one of the classes that the range resolution would be 1% of the wavelength. Now 1% of the 19 centimeter would be 1.9 mm, and the 1% of 293 meter is the 29, sorry, 1% means 2.93 meter, isn't it? So as you could see that for 1% you are in millimeter for carrier wavelengths, carrier phase measurement, and in meters for the code pseudo ranges. So this can be considered as a foundation remark for comparison of code and carrier phase measurement, that the carrier measurements are more accurate and used to achieve much more higher position accuracies than the code measurement. Okay. The best relative accuracies with code measurements are usually a few meters, with carrier measurements usually a few centimeters. Okay. With code observation, a direct measure of the satellite receiver range is attained. With carrier observation, the ambiguity term must be estimated before before anyone may take advantage of the carrier accuracy. That means, what is the importance of the third line is that while performing this carrier phase measurement, although whenever you have receiver you do not know what you are doing inside, but please remember that the carrier phase measurement can only be taken advantage with when you have resolved the ambiguity. And ambiguity resolution is a very popular approach of the so-called in the GPS technique, that within a few seconds your ambiguity would be resolved. So within a few seconds your ambiguity would be fixed, and once it is fixed and an integer value is assigned, then you can simply work with the observables and estimate your unknowns. So ambiguity estimation leads to complexity in the use of carrier phase observation, which do not exist with code observation. That is true. I mean, in your code observation, there is no such additional unknown, while in the carrier phase measurement, you have this ambiguity term. Okay. So advantages and disadvantages are written. You can compare for code and carrier phase. So advantage of code is non-ambiguous and simple. However, for the carrier phase, it is high accuracy potential. Disadvantage is that for the code is that low accuracy, but for carrier phase, it is little more complex. Any question in that? Just observe these statements, and if you have any question, you can ask. Now the question of, yes, if I were at your place, I would ask, sir, what, how do we resolve this ambiguity? If it is to be resolved before we may take advantage of the carrier phase measurements, so how it is going to be resolved? What are the processes? So that ambiguity resolution is a complete independent domain of understanding the so-called estimation of the fixed integer ambiguity. We will discuss that as a separate content, but for that moment you understand that there are various techniques, and one popular technique is the on the fly. There is on the fly named as a technique, which is considered as the one of the best approaches to get the ambiguity fixed within a few seconds. चलिए अब आपके हम लोग डिस्कस करते हैं रिलेशनशिप अमंगस्ट ऑब्जर्वेबल्स एंड पैरामीटर. So for point positioning with code pseudo ranges, can you just understand the first equation which we are writing? It is Pijt plus C delta Jt is equal to rho Ijt plus C delta It. This is the fundamental equation for point positioning with code pseudo ranges. Now what you have to give us in this relationship document, that how many satellites should be there that should be more than the minimum required, isn't it? Because if you have satellite available in your location, you need to have minimum number of satellite that are available, okay, and should be more than equal to or more than the number of observation, number of observable required for, or sorry, number of observable required more than minimum of the number of unknowns. So on the left hand side you have observable, on the right hand side you have unknown. So can you now write the equation if Nj is the number of satellite and Nt is the number of epoch is available? So if you could see that if the 4 satellites are there for one epoch, you will write 4 equation. If the 4 satellites are available for 2 epoch, let's say T1, T2, you will write 8 equation. If the 4 satellites are available for 3 epoch like T1, T2, T3, you will write 3 equation. Sorry, 12 equation. So that means the left hand side is written as Nj cross Nt, that is Nj into Nt, isn't it? It should be more than or equal to number of unknowns, which are 3, that is x, y, z for the position, which is hidden inside this geometric range term. Why it is hidden? Because when you open up this equation, it is the distance equation between 2 points, which is the satellite x minus receiver x square plus satellite y minus receiver y square plus receiver satellite z minus receiver z square. So that means the x, y, z of your the receiver is your unknown plus the clock error, which is nothing but the dependent on the epoch, which is Nt. So can you now write this equation as Nj cross Nt should be greater than equal to 3 plus Nt? Just observe it. So in general, there will be 3 plus NT unknowns with NJ into NT observations. And to get a solvable system of equation, one need Nj into Nt, that should be greater than 3 plus Nt, and we can rewrite the equation which is giving us that Nt should be greater than 3 by Nj minus 1. This is the equation which is coming out of our initial discussion, that Nt should be greater than 3 by Nj minus 1. Once again, I must say Nt is the number of epochs and Nj is the number of the satellite. So if you write Nj as 4, what will happen? Nj would become 4 minus 1, that means 3. 3 divided by 3 would becomes Nt should be greater than or equal to 1. That means if you have 4 satellite, then Nt is equal to 1 or more than 1 is enough to get the solution. But somebody would say, sir, what if we take 2 satellite, Nj as 2, then Nt would be greater than equal to Nj as 2, then Nt should be greater than equal to 3. That means for 2 satellite, how many epochs would be there? 3 epochs. But from considering the geometry point of view, this is not acceptable. We will discuss this geometry aspect when we discuss about the perfect satellite to receiver geometry term, which is called as dilution in precision. So there is a DOP term which will be discussed later on. At that time, you will understand that when satellites are very far from each other, that means with the two satellite, their epochs would be the observation would be coming from very nearby places, so that is not acceptable for getting a unique solution. So in general, 4 satellite with more than one observation epoch are preferred, which suggests that there are 4 unknowns and one need 4 observation. Just observe it. Now there is a term called rank deficiency in GNSS model, where that rank is nothing but the number of linearly independent rows inside a matrix. So if you are writing Ax is equal to B, then X is nothing but A inverse B. So for that moment, for solving Ax is equal to B, for A, the rank should be equal to the number of unknowns. So for SPP using carrier phase, the number of observations are Nj into Nt. That means number of unknowns are 3 receiver coordinates plus Nj unknown ambiguities plus Nt receiver clock bias. The 3 receiver coordinates is XYZ. Nj is number of ambiguities. So there are, let's say, 4 number of satellites. So 4 number of ambiguity would be there. 10 number of satellite, so 10 number of ambiguity would be there. So if Nj number of satellite, Nj number of ambiguity would be there. So similarly, 3 plus Nj plus Nt is the required number of unknowns. Hence, one faces rank deficiency, more unknown parameters than the available observation. For observation equation method, this implies that design matrix A is not at full rank. When I say full rank, that means you need to have more linearly independent rows compared to the number of unknowns. So rank of design matrix, we all know that linearly dependence of two row means that the linearly combination yields the zero. So that is okay. So rank for a quadratic matrix of m cross m rows and columns, if the largest non-singular matrix is matrix A itself, the rank equals to m, and this matrix is regular. So if the largest non-singular matrix A inside a matrix with is m minus 2 cross m minus 2, then the rank of the matrix, the rank deficiency would be of 2, and that will only suggest that the rank deficiency means you need to understand that if these rank deficiency is not removed, that you cannot solve for the solution. So rank deficiency of 2 would be reduced or compromised or solved if you fix certain two parameters. Okay, so this is equivalent by transferring of two of the parameters of the left side of the equation system comprising the measurement. This transfer reduces the columns of the matrix on the right hand side by amount of the rank deficiency. So in case of SPP with phases, one can arbitrarily choose a combination of the receiver clock biases or ambiguities as fixed and solve for the system. Now this is the reason why we are trying to solve ambiguity before or fix ambiguity prior to using taking advantage of the carrier phase. This is the reason, because the moment you have enough satellites, let's say 10 satellites are there, so 10 ambiguity would be there. So 10 plus 3, 13, plus the number of epoch for which you have the observation. Let's say for one epoch you have observation, so 10 plus 3 plus 1, that means 14 unknowns would be there. And how many observation would be there? 10. So every time, the moment you increase the epoch, okay, the moment you increase the epoch, then there is a chance that you would get the your so-called unknown. Okay, so this is the reason, to avoid this rank deficiency parameter, what you need to do, you need to improve the model by fixing certain parameters. So with this, let us discuss the second aspect. So this is the phase equation, which is lambda phi is equal to rho plus n lambda plus delta term. So this is the equation. Again, lambda phi is equal to rho plus n lambda plus delta ij. So on the left hand side, you will shift the satellite clock error, while on the right side, you have the geometric range, you have the ambiguity, and you have the so-called receiver clock error. So now your equation is nj into nt should be greater than equal to 3 plus nj plus nt, isn't it? Now, when you have nj into nt should be greater than equal to 3 plus nj plus nt, what is your take on it? You will rearrange the term, and then nt would become as greater than equal to nj plus 3 divided by nj minus 1. Now, put up the value of 4, let's say. So, nj is equal to 4. If you could just put up the top would become nt should be greater than equal to 7 divided by 3. When you have this value, it should be more than 2. So when you have nj is equal to 4, thus phase model can be used for kinematic provided ambiguity has been resolved by initialization process. Otherwise, what will happen, for every epoch, you can have a new value of the error portion. Just look at this. So it is said that solution for single epoch is possible. Solution for single epoch is possible when the nj integer ambiguities are disregarded. What do you mean by that? Disregarded. Disregarded means you do not consider them as unknown. And when you will not consider them as unknown, when you will have these values with you. That's why in the carrier phase measurement, it is said that during initialization period, you should have the value for ambiguities. Okay. Any doubt in that? Just take a look very carefully. You can observe the equation, and if you have any question, you can simply ask. There is no problem in that. Whatever silly question you may have, you can ask right now.
Sir, what that linearization equation we had derivated last time, sir, will that be applicable for these things also, sir? सर जो अभी हम लोगों ने लिनियराइजेशन इक्वेशन डेवलप किया था सर, जिसमें 4 रोज बनी थी, सर क्या वो मतलब कि यहाँ की कंडीशन के लिए भी एप्लीकेबल होगा?
ये वो वहां के लिए ही इनको जनरलाइज वे में लिखा जा रहा है
सर। हमने 4 इक्वेशंस डेवलप किए थे और
4 इक्वेशन डेवलप करने का मतलब क्या हुआ? nj इज इक्वल टू 4।
यस सर।
भाई ये जो आप लिख रहे हैं यहाँ पर, ये क्या रिप्रेजेंट कर रहे हैं? मतलब कंफ्यूजन क्या हो रहा है, बताइए मुझे, फिर बताता हूँ।
सर कंफ्यूजन ये हो रहा है कि अभी हमने जो उसमें जब हम लिख रहे थे सर, रोज में लिख रहे थे एन, तो सर उसमें लिख रहे थे ना ऊपर में 5ij में 5 1 फॉर 1j1।
तो nj इंटू nt जब आप लिखते हैं तो आप सोचिए, आपने 4 सेटेलाइट ली, एक इपॉक लिया, कितनी क्वेश्चन लिख के आई आपकी?
सर 4 सेटेलाइट और एक सर 4 into 1 हो जाएगा सर।
4 हुआ? 4 हुआ या नहीं हुआ? तो आपने देखिए पीछे जाकर के, क्या आपने 4 इक्वेशन लिखी थी सिर्फ?
यस सर।
लिखी थी। राइट
Yes,
साइड पे आइए, कितने अननोन थे?
सर
हैं?
बता रहे अननोन तो 4 हुए ना सर, 3 XYG एंड 1T।
तो ये तो कैरियर फेस चल रहा है, वरना आप उस पे जाइए अपने कोड बेस वाले में, तो उसमें देखिए 4 ही अननोन आ रहे हैं कि नहीं आ रहे हैं?
यस सर। ओके सर।
चलिए, if there is no question then we can move to next one. तो इस वाले स्लाइड पे देखिए, आपने क्या किया है, एक रैंक डिफिशियंसी इंट्रोड्यूस की है, और किसमें की है? क्लॉक में। दैट मींस यू आर सेइंग दैट फॉर वन इपॉक you are knowing this clock error value, so the nt is written as nt minus 1. So Nj into Nt should be greater than equal to 3 plus Nj plus Nt minus 1. ओके, चलिए अब रिलेटिव पोजिशनिंग के प्रिंसिपल को समझते हैं. नाउ द रिलेटिव पोजिशनिंग इज वेरी सिंपल इन टर्म्स दैट you have a base, you have a rover, and you have a common pair of the satellite. The objective of having common pair of the satellite is that the common observation between A and B or a common error sources will cancel out if we subtract them. So with the help of simultaneous observation at known and unknown points, determine baseline vector between a known and unknown point where one does not solve directly for coordinates of the unknown point. Okay. Instead, you will have baseline vector which is determined, and later on with the help of baseline vector, you can determine the position of unknown point. Okay. So subsequently, application of baseline vector to known point gives the coordinate of unknown point. One can generally form single, double, and triple difference of the code or phase observable. Okay. So typically take difference between A and B as a receiver point and satellite J and K as satellites. It can be done with code or phase observable, and can also take differences between consecutive time epochs. Okay. So just understand, you have a common pair of satellite J, K, L, M. You have two receivers A and B, one at the base and another at the rover, and you can take the measurements from all two positions of the receiver A and B. And what you can do, you can, you know, have this measurements taken at A and taken at B both, and you can subtract them. Any question in the concept? देखिए, आप लोग क्वेश्चन नहीं पूछ रहे हैं. जब वाइवा होगा, जब रिटर्न लिया जाएगा और आप लोग जवाब नहीं लिखेंगे ना, तब हम पूछेंगे कि आपने क्यों नहीं पूछा. इसलिए मैं आपको अभी बता रहा हूँ, जम के क्वेश्चन पूछिए, कहीं कोई डाउट हो तुरंत पूछिए. तो जब आप लोग नहीं बोल पाएंगे तो फिर बड़ी दिक्कत होने वाली है आप लोगों को. So in this case, let's discuss the single difference first. So single difference is nothing but the first observable. The first observable is obviously the code pseudo ranges and carrier phase measurement at in the individual receivers. Okay. So single difference means interstation difference between station A and B for a given satellite J. So you have A and B both as a receiver, and what you can do, you can have a interstation difference, or you can have a inter-satellite difference, that is for J and K for a given station A. Obviously, the second will not have a major role. Instead, the first one, which is the A and B, which is the satellite and receiver A, then the satellite is sending signal to receiver B, and you are subtracting the difference between two observable, which is at A and at B. Why? The satellite clock bias is totally removed and some common errors will be reduced to a greater extent. Why? Because satellite clock, orbital errors, localized atmospheric errors will be same for the single satellite which is giving observation to two receivers. Okay. So model for single difference, that is phi AJT plus F. Obviously the in cycles this equation is written instead of in meters. This equation is written in terms of cycles, and the two equation you can follow from your previous understanding of the code's carrier phase observation. You can write it down again, that phi AJ plus FJ rho J, sorry, phi aj t plus fj delta jt is equal to 1 by lambda rho ajt plus naj plus fj rho delta at. That means carrier phase observable plus satellite clock error is equal to geometric range, ambiguity, and clock receiver clock error. Similarly, for B also you can write it down. The moment you subtract it, the moment you take a difference from 1 to 2, you are performing the single difference. Please remember, the single difference is performed for raw observable. You have raw observable with you and you are differencing these raw observable. Okay. So when you difference phi abj t, that means you are differencing the raw observable collected at B and raw observable collected at A, and you are differencing it. The moment you difference it, it becomes 1 by lambda. The right hand side is 1 by lambda rho B minus rho A, NB minus NA, and delta B minus delta A. It's fairly very clear. There is no problem at all in this. Just understand this. So a system of such equation would lead to rank deficiency even in case of an arbitrary large redundancy. This means that design matrix of the adjustment has linearly dependent columns. And why rank deficiency exists? You are curtailing the number of observable, isn't it? Instead of having the two observables in the first set of equation block, you have now one observable, one deliverable, one final observable that will help us in solving the system. So आप पहले देखिए, आपके पास कितने ऑब्जर्वेबल थे? दो ऑब्जर्वेबल थे. अननोन कितने थे? 3 for receiver B. That means XYZ of receiver B plus the ambiguity curve plus the unknown of the receiver clock. Now here, once you subtracted it down, what you have done intentionally, you have reduced or curtailed the observables. Now obviously that hurts, but what is the advantage? Advantage is certain common error are reduced, certain common sources of errors are vanished, some orbital errors are cancelled out, some satellite clock errors is cancelled out. So single, but obviously single difference is not helping us anymore. Why? Because ambiguity is there, receiver clock error is there, and the geometric term they have inside the component of xyz. So single difference, although you can prepare, but it is not helping you in that much. Obviously, one more thing has happened based on your GDP principle. What you can thought is that error is also increased in this observable. Please remember, when you prepare the z as x minus y, the error in z, be it x plus y, x minus y, or whatever, it will be root 2. Let's say if the error is same in x and y. I hope you get it. The moment you take another form of set of equation by forming this x minus y, the error will also be increased. Okay.
सर
हाँ,
सर अभी आपने बोला ये सिंगल डिफरेंस लेने से कई सारे एरर्स का आपने नाम लिया कि ये सब रिमूव हो जाते हैं। सर हमें ये पता कैसे चल रहा है कि ये रिमूव हो रहे हैं?
नहीं वो रिमूव शिक्षा जी कीजिए। ये रिमूव ऐसे हो रहे हैं कि जो आपका फाइनल ऑब्जर्वेबल आएगा ना फाई ए बी जे, उसकी वैल्यू फाई ए बी सॉरी फाई ए माइनस फाई बी से आई है ना। तो जो फाई ए बी जे होगा वो एक ऐसा टर्म होगा जिसमें एरर सोर्सेस के भी टर्म्स होंगे, जो फाई ए में होंगे, फाई बी में होंगे। व्हेन वी हैव सब्सट्रैक्टेड, obviously we do not know, but instead of solving and for additional terms, we have cancelled it out. You can observe that now while subtracting, the satellite clock error term are simply cancelled out. You do not have to do anything. It is simply cancelled it out. But what I'm trying to say is this is the first step of having this phi abj is equal to 1 by lambda rho abj plus n abj plus fj rho ab. This is the first step of differencing between two observable, although it will not help us in a longer run. Single difference doesn't serve more purpose. What serves the more purpose is the double difference. You will see that. I'll tell you why. But for this time, you just focus on the single difference. Can you write this equation now on your own? Because I want that you should write this equation on your own. Just write the carrier observable for jth satellite and A receiver and jth satellite and B receiver and subtract on your own. I'm again going back to the previous slide. Just write it on your own. Just observe it. Once again, just for your understanding, let me just again inform you that the single difference is the initial step for conducting this relative positioning. Relative positioning starts with this fundamental is that you have a base receiver, you have a rover receiver. You have to compute the position of the rover receiver, knowing the fact that you have multiple other sources of errors also. Okay. Although, as I'm telling you, the single difference is not helping us out in the moment that still there are multiple other components are there. For example, this receiver clock error would be there. Till the time we do not remove it, we have to estimate it by the process. The ideal situation is considered as that when you have ambiguities which are initially resolved, and then you try to solve that model for getting the baseline vector. Any more questions? So with this, we'll stop here. And in the next class, we will discuss the double difference because it needs little more understanding with your single difference background. The double difference observables are the key component for the scientific GPS data processing. So for that, you need little more background. So what I want is that you should go through the literature once again, and I'll upload also there is a Hoffman-Willenhoff book on GPS theory and practice. In that, you will follow these similar equations which are presented here in the literature also, and you will be feel more connected with these content. And at the same time, you could also read the physical significance of preparing these differences. Obviously, as I've told you, if you are working with a single receiver, please understand this very basic concept. If you are working with a single receiver, in order to get a precise solution, you need to either apply certain models to correct for the time being atmospheric error corrections, for the orbital corrections, for satellite clock corrections. You need to apply those individual models. And if you are working with uh, 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 dual receiver, like one you have base and you have rover, then you have the mathematical advantage of working with the observables itself to get the precision standard little more improved compared to the single receiver. So this concept of relative positioning is there to help you out to removing those minimum layer of the error. So let's say if you have a base station and in Prayagraj, and if you have a rover station in Kanpur, this relative positioning won't work because there is a certain range of the distance in which this the errors which are considered to be correlated must have been a proper threshold for this baseline. So let's say for 80 kilometer, 100 kilometer, you can fairly work in this relative positioning. But for distances more than 200 kilometers, you need to incorporate those models which can tackle these large distances. Because ultimately our objective is to improve the precision, isn't it? So commercial software don't help us in that domain because they do not they are not coded or they are not prepared to handle large baselines. Instead they try to encourage to work in a local area, while the scientific softwares are there which help us in solving large baseline of 2000 kilometer 1000 kilometer with precision of millimeter level. That means you can get process a baseline of 1000 kilometer with 2 mm or 3 mm kind of precision. The 2 mm or 3 mm is on your fingers you can measure this distance. This much precision is there if you process with the scientific environment. The reason is simple because they are equipped with various type of modeling environment which are there to handle these large baselines. Okay. Obviously, whenever you subtract or you prepare the the so-called double difference observable or single difference observable, you consider that large portion of the error which is correlated between which is correlated at two places between A and B, that would be reduced, not removed. If that will be reduced to a certain extent.
सर
हाँ
सर जैसे कि रेसिप्रोकल लेवलिंग में करते हैं कॉमन एरर माइनस हो जाती हैं,
हाँ
वही
हाँ,
कंसेप्ट यहाँ लग रही है क्या?
कॉन्सेप्ट वही है बिल्कुल, बट उसको थोड़ा समझने के लेवल को ऊपर उठाना पड़ेगा.
ओके सर.
चलिए, so with this we stop here.